Alrighty, good afternoon, lads and ladies. As people start to filter in, I did just post that link a second ago. I expect it will take a moment. Let me tell you a little bit about where we're going. Sorry, in a bit of a rush this morning myself. Where we're going. We recently learned about antiderivatives. We talked about how to find a function who has a given function as its derivative, right? And we call that the function you're looking for there the antiderivative. Today, and this might seem weird, we're going to talk about something totally different. But I promise that by the end of the week, I will connect the two things back together. So I know you've been working and probably currently are working on antiderivatives in your homework. If you need more time on last week's homework, as always, just request an extension. I think I left it open until Wednesday because there are some of these area problems. And that's what we're going to start talking about today. So for those just coming in, what I was saying is we're gonna change tack. We've been talking about antiderivatives. But today we're going to talk about areas. And then by the end of the week, by Friday's class, I will connect the two concepts for you. A little announcement or reminder. I guess there's two of them. Homework 10 wasn't due today. But is due Wednesday. Now, I know that Wednesday, the other announcement here, there's no class. Wednesday is Veterans Day. So there's no class. The time I have set for the homework to be due on Wednesday is our normal time, right? The class starting time of 12:30. I think what would be most fair and most reasonable given the situation, so I'll do it now, is to reschedule that to 11:59 on Wednesday. So you can work on this thing right up until midnight on Wednesday. Or maybe what I'll do, let's let you work on this until Friday. How about that? This way it will be due, yep. Due at the start of class on Friday. That kind of keeps our normal thing. Our homework is due at the start of class. So I apologize. But that's what makes most sense, right? Now that doesn't mean there isn't going to be any new homework. I will be opening up a new homework set this week probably, but I'll have to think about exactly how to do it. Right now, I just want you focusing on homework 10, specifically the last bit of homework 10, and I also want you getting caught up. So in this class, we really do have like two separate pieces, differential calculus and integral calculus. I talked about this last time we met. This portion of the class that we're in right now is the transition from learning about differential calculus to learning about integral calculus. And it is a great time to get caught up if you've fallen behind on the homework or any of the material, because you kind of get a fresh start with integral calculus. Of course, it does depend a lot on the differential calculus, but it's a nice sort of transition time, which is a good time to get caught up. So those are the announcements. Homework 10, I'm going to push to Friday. I've already done that. It'll be due at the start of class on Friday. There is no class this Wednesday because Wednesday is Veterans Day. If you or any of your loved ones served in the armed forces, take the day off and enjoy the holiday. Today, we're going to learn about areas. Under curves. And we're going to review capital sigma summation notation. In a perfect world, I could trust that everybody knows what this symbol is, knows what it means, know how to use it, but it's not a perfect world. And that may not be your fault. That might have something to do with who taught your pre-calc class. So that's the plan. The main name of the game is what are called Riemann sums. And these are the tools that we use to estimate and eventually calculate the area under a curve, like the area under a graph, y equals f of x. Usually from some point to some other point. Okay. So first I'm going to walk you through a sort of slow discovery of what a Riemann sum is. And then I will write the thing down, and then I will talk about summation notation, and then we'll do more examples. Where to begin? So I give you some function. Some function f of x. And I want to find, or I want you to find, the exact area underneath that curve. So that's, you know, all of this area. That's what I want you to find. Rather than shading that in right now, I don't want to clutter the picture. The question is, how the hell do you do that? How do you find that area? So can we, let's put it up here. Under y equals f of x from A to B. The answer to that question is yes, but it turns out to be a little bit tricky. So we begin with an estimate. We're not going to start out by finding the exact area. We're going to start out with a tool that allows us to approximate the area. And then we're going to use a limit to make that tool exact, to make that estimate exact. So here's what we do. We take our interval and we chop it up into a bunch of little subintervals. In math speak, what we're doing here, this is called partitioning the interval AB into subintervals. So here I have 1, 2, 3, 4, 5, 6, 7, 8, 9 subintervals as I drew it. And then in each of those intervals, I approximate the area under the curve by a rectangle. A we call x0. The right end point of that first subinterval I call x1, and then I label all the others counting up. So x4, x5, this is x6, this is x7, this is x8, and in this case, B would be x9. I want all of these to be of equal length. So you chop the interval AB up into some number of equal length subintervals. The number of subintervals will use the symbol n to represent. And the width of each of these intervals will use the symbol delta x. But before I get into the notation, I want to show you one way that this can be done. So remember what I said, for each of these subintervals, I'm going to use a rectangle to approximate the area. What I'm doing here is building what's called the right hand Riemann sum, because the height of this rectangle, say just this first rectangle, is determined by the value of the function at the right endpoint. And I'll do that for all of these. The height of my second rectangle, I will let that be determined by the value of this function at the right endpoint of that interval. This third guy, again, the height determined by the value of the function at the right endpoint. And I do this for all of these. Please draw this picture in your notes carefully. All right, I'm going to take my time so you have time to take your time. You'll notice that these rectangles, sometimes they underestimate, sometimes they end up being too short, and other times, like right here, and certainly at this endpoint, they're too tall. They overestimate. Now here's the thing. The area underneath this curve is pretty close to the area in these rectangles, right? What's the, if the width of each of these, I'm going to introduce some notation. We call this delta x. And delta x is always calculated as b minus a over n, where n is the number of rectangles we want to use. What's the height of this first rectangle? If this is the graph of f of x, and that height is coming from the value of the function at this endpoint, what is that height? I'm going to scooch this up a little bit. I really do want an answer to this question, so please think about it. Oh, maybe I'm not seeing chat notifications. Yeah, okay. Very good. Right? The y value on the graph right here is f of this. And what's the width of this rectangle? It's true that it is x1 minus a. Remember, the width of each of these subintervals we call delta x. So the easiest way to call it is just delta x. It's the same as x1 minus x0. It's the same as x2 minus x1. It's the same as x3 minus x2. They're all the same. And they're all delta x. So the area of the first rectangle, A1, is its height, which is f of x1, times its width, which is delta x. A2 would be the height of the second rectangle times delta x. What's the height of the second rectangle? The height of this guy. What is this guy's height? Good, f of x2. So his area is his height times his width. Oh, well, his width is the same. It's also delta x. A3, you can probably see the pattern now. The area of the third rectangle is f of x3 times delta x. A4 is f of x4 times delta x. And we can continue this until we get to A9, which is f of x9 times delta x. So all of this together tells me that the total area is approximately the sum of these areas, which is A1 plus A2 plus A3 plus A4 plus all the way out to A9. Is everybody with me so far? Any questions so far? So each rectangle has a height and a width. The area of each rectangle is that height times that width. They all have the same width, but their heights vary depending on the value of the function at the right endpoint of the subinterval. So if I want to know, like, what is the area in A5, I would look at the right endpoint of the subinterval that makes A5, find the value of the function there, the y value on this graph, which is f of x5, and multiply that by the width, which is delta x. I'm realizing this A looks like a delta here. This is an A6. These are all A's there. Now, if you remember your pre-calculus well, you might be able to tell me how I can write this using capital sigma. This would be capital sigma I going from 1 to 9 of AI. This and this mean literally the same thing. The capital sigma here says take whatever's over here and add it up as the variable I goes from 1 to 9. So that would mean take A1, add that to A2, add that to A3, add that to A4 until you get to 9. So this is just a more condensed way of writing this big addition problem. A1 is f of x1 times delta x. A2 is f of x2 times delta x. In general, AI is f of xi times delta x. So that's it. What we've just built here, this object, is called R9. It's the right hand, that's the R, approximation for the area under this curve. I'll give a second for anybody who's still writing. Okay. So this is called R9. R stands for right hand, And the 9 stands for the number of rectangles. And the way I keep emphasizing the word right hand, you can guess that there's also a left hand version of these things. So here, the height of each rectangle was determined by the value of the function at the right endpoint of each subinterval. In general, Rn is the sum from I equals 1 to n of f of xi times delta x, where delta x you always calculate first is b minus a over n, and xi we have to think about a little bit carefully. How do I get to the, say, right-hand side of the 5th subinterval? Well, I start at A, and I walk over 1 delta x, 2 delta x, 3 delta x, 4 delta x, 5 delta x, 6 delta x. So x6, I can think of as A plus 1, 2, 3, 4, 5, 6 copies of delta x. And in general, xi, the right endpoint of the ith subinterval, is a plus I times delta x. This is a formula you will need several times during this homework. You can also write it out in long form. If you want to write it without the capital sigma notation, Rn can be written as, we factor out the delta x, we'll have f of x1 plus f of x2 plus all the way out to f of xn times delta x. If you want to, right? Without sigma notation. If n is small, like 3, 4, 5, I tend to use this form. If n is large, I'll usually use this form. If you're calculating by hand, you'll need to at some point expand into this form. So before I go any further, I'd like to just do an explicit example. And then I'm going to show you the left-hand Riemann sum. And we'll talk about how they're related. The xi's, remember here, this is just a shorthand for like x1, x2, x3, x4. It gives me a way to compute all of the x's that I need in this sum in one place. Maybe one last thing. This piece right here is sigma I from 1 to n f of xi. That's the relationship between the two, right? This is just the long way of writing this capital sigma piece. So this piece on its own could be written like that. And then we multiply by delta x, multiply by delta x. Does not matter what you use on the exam. There will be problems where you need to use the capital sigma version. But on any problem where it's possible to use either, you're welcome to use either. Let's grab an example. These can get pretty gnarly, so I'm going to take it from the book rather than making it up. Here's all the stuff we just talked about. And they're going from 0 to 1 using, how many, no, let's make it a little easier. Rather than going 0, 1, they dive right in, don't they? Okay, we'll do it like this. Let's approximate the area under f of x equals x squared from x equals 0 to x equals 4 using right endpoints and just 4 rectangles. So the way you do this, first calculate delta x. Delta x is always b minus a over n. And remember what a and b are. This is a, this is b, and this is n. A and b are the x values that you're trying to find the area between. N is the number of rectangles you're using in your approximation. So this would be 4 minus 0 over 4, which is 1. And I'm definitely doing that on purpose to make things nice. Second, calculate the xi and draw a picture. We'll put these together. All right, now this picture is not going to be to scale because I want to make things easier to work with. But we'll say x squared looks kind of like this. I'm going to call this 4. So the area that I'm after is all the area in here, right? The area that I'm trying to approximate is all of this area. I'm going to use 4 rectangles and delta x is 4, so I know I'm going to chop this up like this. So my first rectangle, his height is going to come from the right endpoint of that first subinterval. That first subinterval is 0 to 1. My second rectangle, his height is going to come from the value of the function at the right endpoint of the second subinterval. The second subinterval is the interval from 1 to 2, and so on. Okay, here's the picture. Are there any questions about the picture? Where the rectangles are coming from, what they're approximating? I could tell you that x0 is 0, x1 is 1, x2 is 2, x3 is 3, and x4 is 4 just from the picture. But for practice, let's also use the formula. xi is a plus I times delta x. And it's because this formula involves a delta x that we have to find delta x first. Now a here is 0. So this is 0 plus I times 1, which is just I. So x0 is 0, x1 is 1, x2 is 2, x3 is 3, and x4 is 4. You notice that I have one more of these xi's than I have rectangles. So one of these is not going to be used in this right endpoint calculation. x0 is not the right endpoint of any of these. So these are the ones that we will use for R4. All right. The area is approximately equal to R4, which is f of x1 plus f of x2 plus f of x3 plus f of x4 times delta x. So here I'm not using the capital sigma version because n is small and I need to do the calculation by hand. So I'd have to write it out eventually anyways. This is the height of the first rectangle, height of the second, height of the third, height of the fourth. So the area of the first is f of x1 times delta x. The area of the second is f of x2 times delta x, and so on. I've just factored the delta x all the way out. x1 is 1, so this is f of 1 plus x2 is 2, so this is f of 2. x3 is 3, and x4 is 4. So those are what I'm plugging into my function. Delta x also is 1. So I'm going to stop writing the delta x in the next line because I know that it's 1. There's no reason multiplying by 1 it's not doing anything. And now what is f of 1? Well, what is f of x? F of x is x squared. So f of 1 is 1 squared. F of 2 is 2 squared. F of 3 is 3 squared. And f of 4 is 4 squared. And this is all being multiplied by 1 because delta x is 1. And then that sum, 1 squared plus 2 squared plus 3 squared plus 4 squared, that's 1 plus 4 plus 9 plus 16, which is 5 plus 9 is 14. 14 plus 16 is 30. So the area under the graph, y equals x squared, or f of x equals x squared, from 0 to 4 is approximately 30. This is an example of the type of calculation and picture you will be expected to create for your homework. I've said it before, WebAssign cannot force you to draw the picture. It can only make you select from the pictures. Make sure you're actually drawing the picture. All right, this step where you draw the picture, really big deal. What we did from here is then just use the formula. All right, right? Step 3, where we actually do our calculation, is just using the formula for Rn. We just plug into the formula for Rn. Questions on the calculation, the picture, any of the formulas? Okay, if you don't have a question for me, I have one for you. Is this correct? Is the area under that graph exactly 30 square units, or is it something else? Very good, Harris nailed it. The area under the graph is not exactly 30. It's definitely less, because look, this rectangle is bigger than the area in here, right? The area of this rectangle is way bigger than the shaded area. The area of this rectangle is bigger than the shaded area. The area of this rectangle is bigger than the shaded area. Each one of these rectangles is overestimating. So this is an overestimate. The actual area is smaller. I'll teach you how to find the actual area eventually, but first we need to get good at this approximation, because what we're going to do is we're going to take a limit and use more and more and more and more rectangles. So we'll need to find a way to come up with a nice formula for this answer as a function of the number of rectangles you're using. And then we're going to send that number of rectangles n to infinity. Before I go into more detail about that though, I want to introduce the left-hand Riemann sum. And I'm going to do it first by looking at this same example from the left-hand Riemann sum perspective. And then I'll give you the formula for that. Any questions at all on what we did here before I move away? Okay. Same problem, but now we're going to estimate the area under f of x equals x squared from x equals 0 to x equals 4 using left endpoint and 4 rectangles. Now, I haven't given you a formula for this yet, so we're going to need to follow our nose. And then I'll give you a formula for Ln, which is like Rn, only left instead of right. First, I just want to go through this example. Your first step, as always, calculate delta x. If you think about the picture, it's still this function, still from 0 to 4, still 4 rectangles. So delta x is still going to be 1. But you can always use this formula, b minus a over n. A, remember, is always the smaller of the two x values. B is always the larger of the two x values. N is always the number of rectangles. So this is still 4 minus 0 over 4, or 1. The xi's are still following the formula a plus I delta x. A is still 0, delta x is still 1, so this is still I. So x0 is 0, x1 is 1, x2 is 2, x3 is 3, and x4 is 4. Let's draw our picture. Weird hair floating around. So again, I'm trying to find the area under here. So I'll chop this up. Only now the height of each rectangle is determined by the value of the function at the left end point. So my first rectangle, his height is 0. My second rectangle will look like this. My third rectangle will look like this. And my fourth rectangle will look like this. See the difference between the right and the left? It's somewhat subtle. The xi's which I need to calculate the left-hand Riemann sum are these ones, which are not the same ones that I needed for the right-hand Riemann sum. So L4 is the name we give to the approximate area based on 4 rectangles using left endpoints. Again, the area that I'm trying to estimate is the same area as before. It's all the area under the curve here. And now my estimate is going to be an underestimate. L4 is f of x0 plus f of x1 plus f of x2 plus f of x3 times delta x. So instead of having 1 through 4, I have 0 through 3, because the left endpoints of these subintervals are 0, 1, 2, and 3, rather than 1, 2, 3, and 4. Now this is, if I plug in x0 is 0, so this is f of 0 plus f of 1 plus f of 2 plus f of 3 times delta x, which is still 1. And we can calculate. F of 0 is 0 squared plus f of 1 is 1 squared plus f of 2 is 2 squared plus f of 3 is 3 squared, and 1 is 1. So this, whatever it is, it's 0 plus 1 plus 4 plus 9. That's 5 plus 9 is 14. And this is clearly an underestimate. The only way I can tell it's an underestimate is from the picture, right? There's more shaded area than there is area in those rectangles. So R4 was 30 and this was an overestimate, and L4 was 14, which is an underestimate. If I want to try to get at the actual value of that area, I know it's going to lie somewhere between 14 and 30. But I don't know exactly where. It's hard to say. I could use more rectangles. That's one way to do it. Or I could try a different method. I could try averaging R4 and L4. And that, it turns out, will give you what's called the midpoint, which we would call M4. So the midpoint, one way to try improving this is to average these. And we call that M4. M4 is the average of R4 and L4, which is 1/2 R4 plus L4, which is 1/2 of 30 plus 14. 30 plus 14 is 44. Half of that is 22. So now I'm going to give you the formula for Rn, Ln, and Mn. This isn't the only way to get Mn, by the way. It just turns out that if you were to use the midpoint for each of your heights, you get exactly the average of what you get if you use the right and the left. Okay, before I move on and give you all these formulas in one place, are there any questions about what we did here? Here's step 3. Not necessarily, Josh. That's a really good question. Is the error the same in both? Like, is the overestimate too much by the same that the underestimate is not enough? And the answer there is no, not necessarily. It's also, while we're here, not always true that the left is an underestimate and the right is an overestimate. For this function, that was the case because this is an increasing function. So for an increasing function, the left endpoint will always underestimate. And for an increasing function, the right endpoint will always overestimate. But if your function isn't always increasing, if it turns around, then it's not immediately clear which one is an overestimate and which one is the underestimate. I will give you several formulas for Mn. The easiest way to calculate Mn is to calculate Rn and Ln and then average them, but it's not the only way. And I want to make sure you understand why we use the M here, why we call it a midpoint. So I will draw some pictures and try to make all of that a little bit more clear. But you can always calculate M4 as the average of R4 and L4. That will always work. It's just not the only way. Good questions from Josh and Andrew. Any other questions? Okay. So, formula time. The formula for Rn you already know. These things are called Riemann sums. Rn, as you know, can be written as sigma Oh, I shouldn't use an N there. Sorry. Rn is sigma I from 1 to n f of xi times delta x. And if you want to write that out without the sigma notation, that is f of x1 plus f of x2 plus f of x3 plus all the way out to f of xn times delta x. Ln is the sum from I equals 0 to n minus 1 of f of xi times delta x. Just this very subtle change. Instead of going from 1 to n like you do in Rn, you go from 0 to n minus 1 for Ln. And this can be written as f of x0 plus f of x1 plus f of x2 all the way out to f of x n minus 1 times delta x. And we have the pictures. I'm going to draw here the picture for Rn. So we chop this up into subintervals. And then we use the right endpoint of each subinterval to determine the height. This is for Rn. The picture for Ln is very similar. We chop this up into a bunch of subintervals. But now we use the left endpoint of each one to determine the height. So each height now coming from the left endpoints. The midpoint rule is its own thing. And to help you see this, I'm going to draw this picture a little bigger and with more accentuated curvature. Same deal, we're going to chop it up into a bunch of subintervals. But now from each one of those subintervals, I find the middle and I use that to determine my height. And it just turns out that this is the same as averaging the left and the right. This is the picture for MN. And MN happens to be the average of Rn and Ln. Now, finding each of these midpoints is kind of a pain in the ass. So usually, if we want Mn, we'll find Rn and Ln and then calculate their average. But it's up to you. Everywhere here, delta x is always b minus a over n, and the xi's are a plus I times delta x. So those top two formulas are the ones I want you to pay attention to. The midpoint rule is neat, and in Calc 2, you'll talk a little bit about approximate integration methods and how you can make them better. One of the ways to improve on Rn or Ln is to use Mn. But I'm only giving you one problem that involves the midpoint rule. The rest are just Rn and Ln. Questions on the notation for these formulas? What they mean or how they connect to the picture?
So if the graph were to like pass and intercept the x-axis and make a go into the negative, the area would still be considered positive, or do we make that negative area?
That's a good question. Area that's beneath the x-axis will be measured by these as being negative. And that's okay, that's how we want it. If you have a function that spends some time above the x-axis and some time below the x-axis, you have to discern between calculating Rn or calculating Ln and finding the exact area. Area itself is always positive, but the object that we're going to construct here, which is called a definite integral, measures area together with the sign. So if it's below the x-axis, normally we'll measure that as negative. If it's above the x-axis, normally we'll measure that as positive. So it's a really good question. Other questions here?
What happens if it's kind of involving like a graph that goes to infinity? Can we just say like, nah, area does not, or I don't know.
Yeah, if you want to find the area from some number all the way out to infinity, come see me in the 6th week of Calc 2. We will address that, but not in this class. Those are called improper integrals, and it can be done. And sometimes those areas are finite. Sometimes those areas are infinite, but we won't be addressing that in Calc 1.
Okay, so then we won't even see anything like we're saying, hey, between A and B, and if between A and B there's like a hole or something weird going on, we will never encounter that here.
Well, a hole is okay. In fact, the function f of x, in order for the definite integral to be defined well, doesn't need to be continuous. But for us in this class, we will use piecewise continuous functions. So it could have a jump, could have a hole, as long as it's nice everywhere else. But it won't have any vertical asymptotes, and you won't go off to infinity in the horizontal direction either. So these areas will always be well defined for us. Other questions? All right, let's try 1 or 2 more examples. We can return to the problem of the area under x squared from 0 to 4, but maybe we use more rectangles. Let's do R16. That's going to be a lot to do by hand. Let's do R8 for f of x equals x squared from x equals 1 to x equals 4. This time I'm not going to draw the picture. When R is small, you should always draw the picture. But I'm not going to draw the picture this time. I'm using a larger n here. We've drawn the picture of x squared a few times. So I just want to see what the result is. First, I calculate delta x. That's b minus a over n. In this case, that's, oh, I said 1 to 4. I want to do 0 to 4, sorry. That's 4 minus 0 over 8, which means this is 4 over 8, or 1/2. Then I calculate my xi's. Xi is a plus I delta x, which is 0 plus I times 1/2, or I over 2. And the formula for R8 is, I'll write this one in sigma notation. The sum from I equals 1 to 8, f of xi times delta x. That's just the formula. So now let's start plugging in. That's the sum from I equals 1 to 8. What is xi? The thing inside of f here. Xi is I over 2. And what is delta x? Delta x is 1/2. Now, it's a rule of the sigma operator that constant multiples can come out. So this is the same as 1/2 times the sum from 1 to 8 of f of I over 2. F of I over 2 is I over 2 squared. And this can also be simplified. So we're getting practice with our sigma operator now. This 1/2 is this 1/2. Then I have sigma I from 1 to 8. Inside my sigma, I have I over 2 squared. Well, I over 2 all squared is I squared over 4, which is 1/4 I squared. So here, just a little bit of algebra on the side. So in here, I have 1/4 I squared. And just like the 1/2 came out earlier, this 1/4 is a constant multiple. It doesn't have any i's in it. So that can come out. 1/2 times 1/4 is 1/8. So I have 1/8 sigma I from 1 to 8 of I squared. And doing all of this algebra inside the sigma operator before writing things out will make it easier to compute this. Let's go ahead and now write this out. The 1/8 is there, and then the sigma I from 1 to 8 of I squared is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared. There is a formula for calculating things like this. And that formula is one of the important things that you guys are going to be learning. I'm going to use the formula here, and then after we finish with this example, I will tell you what it is. In fact, instead of using that formula, since you don't know it yet, let's go ahead and grind it in decimals. We can use the scientific calculator for this. I don't think I need the percent, the parentheses, right? Yeah, I think it'll work okay with that. All right, so 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared, which is the sum I needed, is 204. So this is 1/8 times 204. And if I divide 204 by 8, we get 25.5. So this is a reasonable estimate for that area. I've used 8 rectangles, n is getting bigger and bigger. And the larger n is, the more rectangles you use, the better your approximation will be. These pictures with more and more rectangles are harder and harder to draw by hand. However, your textbook has some good pictures that I will show you in a second. Before I do that, I'd like to field questions on this algebra I did with the sigma operator, everything up to here. I know it's probably been a while since you've seen one of these things. I know they're kind of scary. Whenever they want to show scary math in movies, it's always these things floating around. So what are we wondering?
You mentioned earlier that there's some times where we should be only able to use this stuff instead of the long way that the other way that we could have done it. What's the situation where we have to use this way?
When you don't know what n is.
Okay.
If I ask you to calculate Rn in general as a function of n, then this would be an n, and your sum would go all the way out to n terms. There's no real nice way to handle that in the long form here. All right, like if this sum had to go all the way out to n squared instead of going to 8 squared, where n is a variable, then you don't know how long to write. You can put some dot dot dots in and make it work like that, but it won't help you calculate the sum. So in those situations, we will be reducing to something like this, and then using one of the formulas I'm going to give you in a minute. question. Do you think this is an overestimate or an underestimate? It's still not exact. It's closer, but is it bigger or smaller than the actual area? Yeah, still an overestimate. Good. Yep, everybody nailed that. So before we move on, I'm going to give you some results down here, but before that, I wanted to show you some pictures. So here's left endpoints, here's right endpoints. You see with the function being an increasing function, the left endpoint method underestimates, the right endpoint overestimates. And here what you'll see is the more and more rectangles you use, the better and better your approximation gets. All right, here's that picture again. More rectangles. This thing looks real damn close, right? The area of these rectangles is almost exactly the area under the curve. There's very little poking up above and very little poking down below. R50 is still an overestimate, but not by a lot. L50 is still an underestimate, but not by a lot. And the conclusion that they draw here, that right endpoints will always overestimate because this is an increasing function, and left endpoints will always underestimate because this is an increasing function. That's true in general. And the way they attack this in general is the way I've described. Nothing magic. As you use more and more rectangles, your area gets better and better. Here's your general formula for Rn. Here's your general formula for Ln. And the midpoints, you can actually use whatever points you want to sample. But we're not going to go into this any more detail than we need to, so don't stress about that. And what else do we want here? Yeah, so we're there now. I'll go ahead and give you the formulas. Maybe before the formulas. No, this is the right time. Okay. So some summation formulae. The sum from I equals 1 to n of I. This is 1 plus 2 plus 3 plus n minus 1 plus n. If you just add up the first n numbers, this is n times n plus 1 over 2. There's a neat proof of this. If you take the last one and the first one, they add up to n plus 1. If you take the second to first and second to last one, they add up to n plus 1. So you can keep pairing all of these. Each one of the pairs adds up to n plus 1, and there's n over 2 of them. The sum from I equals 1 to n of I squared, which is 1 squared plus 2 squared plus 3 squared plus n minus 1 squared plus n squared. This is, I don't want to fuck this up, 2n plus 1, 2n minus 1, I forget. Let me see, we should give it to us 2n plus 1. No, they might not give it to us here. All right, sorry. Some of n squared. There's it's the same as the previous, just with a 2n, yeah, okay, 2n plus 1. I always forget 2n plus or 2n minus. So this is n times n plus 1 times 2n plus 1 all over 6. And the last guy that you may end up needing is the sum from 1 to n of I cubed, which would be 1 cubed plus 2 cubed plus 3 cubed. Second to last term would be n minus 1 cubed, and the last term is n cubed. This turns out to be the square of the first guy. N times n plus 1 over 2 all squared. So these are useful formulas. They can save you time when it comes to stuff like this, right? Instead of writing this out using Desmos or, God forbid, calculating it by hand, I could apply the second formula here. And we can check that n times n plus 1 times 2n plus 1 over 6, when you plug in n equals 8, really does give you 204. Let's do that just for fun. So what did we say? We had n, so that's 8 times n plus 1 times 2n plus 1 all over 6, 204. So the sum of the first 8 squares is the same as the formula I gave you with n equals 8 plugged in. So we can save ourselves the headache of ever having to do this and just do this instead. Not too bad, right? If I have to do something like this by hand, this is how I would do it, especially if n is large. Okay, we're getting towards the end, but we're not done yet. What's the actual area? Well, I want to use all the rectangles. I want to use infinitely many rectangles. You can think about the area under the curve as really being infinitely many rectangles. Let's come back here. The larger n gets, the better this approximation gets. So this approximation will become exact as n goes to infinity. So you take the limit as n goes to infinity in Rn, or you could use the limit as n goes to infinity in Ln. Either one will work. If you plug in for Rn, this is either the limit as n goes to infinity, sum I from 1 to n, f of xi times delta x, or limit n to infinity, sigma I from 0 to n minus 1, f of xi times delta x. And if you really want to plug everything in, have one formula that really gives you it all in one go. This would be the limit as n goes to infinity, sigma I from 1 to n, f of what is xi? It's a plus I delta x times delta x. And over here, this one, if you really wanted to boil it all down into one thing, would be the limit as n goes to infinity, sum from 0 to n minus 1, f of a plus I delta x times delta x. There are some problems in your homework where I give you something like this, and I ask you, what function is it measuring the area of? It's measuring the area, so you have to figure out what the function f is, and you have to figure out what the interval a to b is. The a to b, you'll get those by thinking about delta x, and maybe this thing. And the function f you'll get from the overall algebra shape of the piece inside the capital sigma. This object has a special name, but we're not going to name it yet. It's an integral, And I'll give you notation and everything you need for that, but not today, because today you already have plenty on your plate. Okay, how are we doing on time? We are out of time. So this is where we're going to stop for today. I will pick it up here on Friday, but you now have everything you need and a little bit more to finish up the homework that is open. Any parting questions? Alrighty then, I am signing out. I hope you guys have a lovely rest of your day. Finish up homework 10. And on Friday, we will talk just a little bit more about how to calculate these exact areas. You only have one problem like that on your homework, and you can solve it following everything that we did today. And I'll show you the connection between these things and what are called definite integrals on Friday. That is it. I have a normal office hour today from 3:30 to 4:30. If you need to reach out to me, feel free to do so via the office hour, Canvas messages, or emails. Exam grades will be in by Wednesday. Take care, guys.